ready when others are. I should speak for about an hour.
He's the boss. He's
Excuse me.
Okay, so what do you do? That?
Yes.
Okay. Okay, so thank you for coming here. Today we have Donovan here, who will speak about simplices in the Calabi-Yau web.
Thank you. Thank you to my hosts. I'm not sure I've met you all. Thank you to Michelle for the invitation. Nice to be here for the week. This is work in progress, part of a project with Tatsuki Kuwagaki and Weilin. And I hope it will be a fairly gentle introduction to the study of some singularities in algebraic geometry, a mirror symmetry story for them, and try to understand derived categories of coherent sheaves associated to them. So let me introduce those singularities, and we'll study them from various points of view. So, a family of singularities in dimension D, and we'll start with D equals 3. So I think this one will be very familiar from various points of view. And indeed, this one is very well studied. The point of the talk is that its immediate generalizations become substantially more interesting. So we take this, two-dimensional vector spaces VI. So our vector spaces will always be two-dimensional in this talk. They're tensor product and vectors of this form. So that makes a cone in a 2 times 2 equals 4 dimensional vector space. And there are various ways we could view this. We could view it as singular 2 by 2 matrices. If I do elements of that tensor product of matrices and say A and J, and as we all learn at school, that's equal to the vanishing set of this determinant function for A1, so A11, A22 minus A12, A221. So I've taken the determinant and taken the diagonal and anti-diagonal elements, of course. Okay. So there's this, but to continue our sequence, we take ZD. So this is D-dimensional, not quite obviously, but we'll easily see. If I now take a D minus 1-fold product of vector spaces, still dimension 2, and I take vectors in there of this form, then this again gives a conical singularity, a larger dimensional vector space. And what is it? Well, in these terms, we could say it's simple 2 by 2 by 2 hypermatrices. Just a word for elements of this tensor product, and they're rank 1 in this sense. So, as an algebraic geometer, you might think of it most easily as cone on this. So product of P1, let's work over C. The Riemann sphere, projected line over C, product of that d minus 1 times, that naturally embeds into a higher dimensional projective space, and we can form a cone. And so that's one way to see that this is indeed a dimension D. And now to extend this description is perhaps surprisingly a little complicated. And so I wanted to show just dimension D equals 4. So Z4 is 4-dimensional in C 2 times 2 times 2, 8. And what are the equations that cut it out? Not just one, but my hypermatrix AIJK has Cayley hyperdeterminant. So this goes back to the 19th century, but is not taught in school. You perhaps understand. It's quite a beautiful thing. So I'm going to take the following degree 4 polynomials in the entries. So how to see it? This is my hypermatrix. So imagine the elements in here. What I've done there is taken a solid diagonal and made a degree 4 monomial for that. And continuing, see, this is a visual. Yeah. So this one, this 1 0 0 1 1 0 this is a diagonal square, and this so yes, so if I got it right, these correspond to a tetrahedron. Yes, the bottom there. So it's a quite lovely thing. We have, let's see, 4 solid diagonals and 6 pairs of base diagonals, giving those diagonal squares, and then 2 tetrahedron embedding like that. Yeah, and I suppose I should say, so we have this this hyperdeterminant equation plus 3 more which are essentially the two-dimensional determinant in different directions. So we have this contrast between how easily we can parameterize this singularity by these vectors W, and how it's perhaps surprisingly difficult to write the equations for it. I mean, problem of writing down the equations is beautifully solved in generality by so Gelfand, Kapranov, Zalabinski. So this is an example of their theory of discriminants determinants, and first of a similar panel. So that's the starting, and it will come back, this theory of GKZ. First, I want to show some natural spaces related to the singularity, some natural resolutions, which we'll be studying the geometry of. So, solution of xi for each of these CD. I'm going to show maps xi to zd which will contract some exceptional locus a product of projected lines still over C, and we'll find these for such a line. So write down here and see how far I can get.
So,
Yes, please. Yes. So this,
these all affine.
so yeah, so they're affine, so they're in a singular sense Calabi-Yau. We're going to produce these small resolutions with the Calabi-Yau.
These still won't compact.
They're not compact, but they can be compactified in many ways. So this is the generic singularity you find on a Calabi-Yau viewpoint. The idea of choosing this is it's one of the most generic singularities you find on a Calabi-Yau. So if you allow singularities, but these singularities can be resolved, and that's what we're actually going to study. So yeah, I will. Oh, I shouldn't do that. So I've avoided compactifying because it makes things hard to state, but that is okay. So for t equals 3, these resolutions, for instance, xi, can be described in the following way. I don't know how much this will suit people necessarily, but if I take one of the vector spaces and projectivize it, that gives me a particular copy of the projected line. And that has O-1, so a twisting sheaf and a non-trivial standard bundle on it. And I can tensor with the other vector space V1 to give a rank 2 bundle. So we notice this is a three-dimensional total space, and that there is a morphism to this singularity. So, let's see.
And V1 will be degree -1.
So this rank 2 thing becomes by degree -1.
Yeah.
So that's one way to think about it. The other way to think about it is a point in this line bundle is a line in V2 and a point on that line, which we then tensor with an element of V1, which gives a point there. And you can go backwards, except if you're on the zero section of this bundle. So the zero section of this bundle all maps to the singular point. So that's the construction. And let me write x2. So we just swap the rows of V1 and V2. Now,
I'm very curious, can you
Yes,
say
right.
like, I don't know, O plus or -2, or like, OA plus OB for A plus B plus.
yes, you can. And so what are the characteristics of this situation? So this is a P1, which is in some sense the simplest thing you can have. And if I'm going to have a rank 2 bundle, and I'm going to be Calabi-Yau, then the degrees must add to -2 canonical class of this. So indeed you could have -2, but then you'd have to have 0, and your curve would no longer be rigid in that direction.
So it won't arise as,
It's a different thing.
it's a different thing, okay, thank you.
But there's a theory there, which I'm currently avoiding. Okay, and so maybe let me just say the words that I have a birational map between x1 and x2, and this is called the Atiyah plot, and it replaces PB2 in here with PB1 in here. So it's a classic birational map. And so now, if v equals 4, what do you have? Well, let's just give x1, because the pattern I think will be clear. I take the total space of v1 tensor -1 -1 on PB2 times PB3. Okay. So I hope we can imagine the same trick. So this ruled surface with a rank 2 bundle over it has a map to Z4, and it's just contracting the zero section, exceptional surface. Now we get something a little more interesting. We get x1, x2, and x3. So maybe if I write, so each of these xi's is given by cycling. And cycling the indices that appear here. And now I have 3 small resolutions. Yeah, so let me emphasize that these are all non-compact Calabi-Yau. And I have these plots between them. So these are all now family versions of this classic threefold plot, where the base is one of the projected lines appearing.
Is that like a variation of GIT picture? Yeah, this one.
Yes, it is. So you can make, so this is all toric, and indeed, it's a toric BGIT.
But does it look like a planet P2? And then I cycle around. Like what is the chamber structure?
So the chamber structure is the A2 hyperplane arrangement, but with a quotient action, because so that has 6 chambers, and the corresponding pairs, the phases I'm writing down. Any more at that point, or maybe online?
I would propose maybe to go down a tiny bit,
Okay,
just one.
right.
The quotient is by, it's like a Z2 quotient, right?
Yeah.
So do I have to choose one of the roots to?
So
It's not the full wild root, right?
so because I've not worked out a higher example, I'm not quite sure what it is exactly. But the point is that I've chosen an ordering of these by saying cycle.
Ah, okay. So
So
there are 6 chambers, but somehow there's redundancies.
yeah, exactly. And that goes to higher temperatures. I didn't quite work out the details. Yeah. Okay, so let me state the general picture then. We have a D-2 simplex of birational maps. They're all dominated by the same thing. Or let B, the blow up of this VB at 0. So that introduces a divisor, and that's not Calabi-Yau, but it dominates this simplex of small resolutions. So that's the setup. And now we try and say something about the derived categories of these Calabi-Yaus. And we'll relate it back to GKC. So
is the exceptional divisor of B like isomorphic to P1 to the D-1?
yes, that is actually that.
Okay, and then I just project onto the various factors.
Exactly.
Okay.
Yes. So the blow up of the apex of the cone introduces that, and then you project. So and then you have to check that the bundles go with you, if they do. So it's not too surprising, and it can be proved in a bunch of ways that the derived categories of covariance views on these xi's are equivalent. And what we'll be doing is looking at the relations between these equivalences. And these correspond to every edge of the simplex. So I can look at derived categories on either side. And just for this functor, say it's via dB, by which I mean I have a functor that pulls up to B and a functor that pushes down, a functor between derived categories, and together they make an equivalence between these Calabi-Yau derived categories. So the threefolds, this follows from general theory. But in general, it follows, as Navi was saying, from birational torque, VGIT. So this is very standard, and there's some decategorification of this. Yes, please.
These are not smooth.
This is not smooth, but these are. And that's part of the reason why we're studying these as a substitute for this. So, yeah, so indeed, this works on whichever version bounded and unbounded. Although I want to take bounded. What I'm about to say, which is that if I look at the Grothendieck groups for these two, so let me give some quick definition of this, because we're smooth. I can describe this abelian group as generated by it's not such a good way to write it. So not the set, but the abelian group generated modulo a relation that a bundle of E plus a bundle F here is equal to extension, any extension of E by F. So given a sheaf on X, as it's smooth, we can resolve by bundles, and cutting up into extensions, we can get a class. Or generally, we can take at least a bounded complex and do the same thing. And therefore, this functor F will induce an isomorphism on these K groups.
Can I ask a question?
Hey.
Hi, this is Tyler. So is in this VGIT problem, do you have any chambers that aren't this type? Or are they all derived categories of some xi?
So all the open chambers correspond to some xi.
Okay. And the other question I have is this some quasi-symmetric case?
Yeah, good question. So in dimension 3, it's quasi-symmetric. In higher dimension, it fails.
Okay, great. Thanks.
Yeah. We'll come back to that for those that maybe didn't understand that point. I see. Okay, so we have these isomorphisms between K groups, and we'll use them once I've explained the relevant Gapranov-Zelvinsky stuff with this set of examples. So C star acts on vector space 1 and vector space 2. And this gives us GIT quotients x1 and x2. So this geometric invariant theory is a way to make a quotient for this action, which node is not free, by throwing away certain points. And all we need to know is that in this case, the point is thrown away. I just want to give this here. And when we talk about variation of GIT, we mean changing a stability condition in this construction to give either x1 or x2. Okay. So, as we said, this is a toric setting, and there's a standard way to write down the toric data. So you'll see the outcomes of this machine, most probably. So a short exact sequence of abelian groups. The first one, first morphism, 1, 1, minus 1, minus 1, corresponding to these weights. Remembering those vector spaces are both of dimension 2. And then the cokernel. So let me present the cokernel. Let me choose a basis here. Let's write it as 1, minus 1, 1, 1, 1, 1. So clearly a cokernel to the A data in toric convention. And there's a number of things we can do with this. So we could view this matrix as 4 vectors in 3 space. And if I drew them in the right basis, I would get what's called the toric plan. And so this is the toric fan for the singularity Z. And the resolutions x1 and x2 are given by triangulate. So dividing this square cone into 2 triangular cones. So that's one thing that we can make from this, this data, and that gives us lots of intuition into these examples. We can also make a GKZ system of differential equations, which is quite mysterious to me. So, one goal for this course is this talk is to demystify this in this example. Just for d equals 3 first and indicate what happens for higher dimensions. This is really a nice set of examples in that way. So a system of differential equations. Let me write it down in a slightly abbreviated way, but I hope it will be clear. So I have a function of 4 complex variables, where these are thought of as coordinates on a torus T, which is obtained from this abelian group C4. So I tensor that with C star, I get a complex 4 torus. So we think of those coordinates as living here. So which one the dual attached, apologies. And this function should be filled by the following differential operators. So d1, d2 minus d3, d4. So that's coming in an obvious way from this vector. But from this matrix here, I make the following: Z1, D1. So D1 is differentiating with respect to D1 minus Z2, D2. Z1, D1 plus D3, D3, Z1, D1 plus Z4, D4. And here I'm going to put parameters. So these are just complex parameters. She has a family of systems of partial differential equations, like so. So these 4 equations for this function in four. So that's the GKT system, and it simplifies quite beautifully in this case. Well, if I take just Z1, so I'm setting all the other Z's to some fixed thing. So I just have the function of Z. So this choice corresponds to a splitting here. And now I just have one differential operator, D equals D1. And I get just substituting into this first differential operator here. I get the following. Right. And some simple manipulations is something which you may be familiar. D minus D squared minus alpha 1 minus alpha 2 plus alpha 3 plus 1 B minus a constant. And so this now is just the Gauss hypergeometric equation.
Solutions to what are solutions to that?
So solutions to that are Gauss hypergeometric functions. So it's unhelpful.
Yeah, but like in that, like what is it computing or whatever in the context of
Yes,
this quotient? I guess that's the next thing you're gonna
that's
say.
exactly what I said.
It's too eager.
Yeah. So let's go on to that.
Sorry, why did you say f of z equals z1? I think I missed the logic.
Yeah, and I got it a little bit out of order.
Okay.
But I should have said choose a splitting.
Uh-huh.
And that corresponds to picking one of these coordinates and setting the rest to a constant. So that'd be right. C2, B3, B4, constant. Okay. Is that a bit clear enough? Yeah. Okay, great. Thanks. So I wonder if I can go down here. So So this is of use because the domain of F is Z complex numbers minus the roots of this, which is 0 and 1. And this appears in mirror symmetry theory as the stringy Taylor moduli state. So this is an example of a stringy Taylor moduli space M. And we expect that loops, the fundamental group on this, acts on the derived categories of my xi, and by the same means as on the left, these induce an action on the basin.
And so that's the stringy Taylor moduli of like O minus 1 plus O minus 1, or
Yes.
of x1
Yes.
x2, x1 versus x2.
So this is the mirror symmetry expectation, and that this action categorifies monogamy for this hypergeometric system S. Let's say this is S. And we'll give a series of such systems.
So am I supposed to expect that S is the same thing as like the broken connect, like the quantum connection that you get in quantum homology?
Yes.
Okay. Is that proven, or is that just a like in the toric case? Is that known?
Not sure. Not sure. I suspect so. Yeah. So, yeah, it's more about understanding these particular examples. Then, yeah, I don't think we're saying anything more than that. Okay, let me work out how to speed up a little. So, sketching this out for our first two examples, d equals 3, my moduli space M, I'll write it like this because it's part of the pattern, is P1 minus 3 points. Okay, so let me draw it like this. So let me take P1, a sphere, and remove 1, 2, 3 points. And let me put two derived categories here. Then this action star can be induced in the following way. I take plot functors to and back, and I take line bundle twists acting on the derived categories on either side, and the monogamy around the polar holes. So in this case, star is folklore. It's been known for some while. And it's this picture. So this includes a claim that all these functors are related in a way that means when I compose them all in the right way, that's a null homotopic loop. and it induces the right relation between those functors. And this relation with the monodromy of the hypergeometric system is the following, that in this case, S is Gauss, so that, and this Gauss system has two independent solutions F of this equation. Yeah. Whatever the these generic values of the parameters, and if I take a point here, so considering that as a z up here, and I work out what the monodromy around with these loops is for my two independent solutions, then I get some 2 by 2 monodromy matrices. And these can be viewed as operators on the K-theory, KXI. So this is indeed rank 2 in this case. So maybe it helps. So generators of the K-theory are just O and O minus 1. So for each of these loops, we have some matrix acting on K-theory, and it corresponds to a classical, known to Gauss, monodromy matrix. These
Will,
yes, please.
I have more questions now.
Right.
So I'm used to this hypergeometric to be telling me about periods in the B model. And now you're giving auto equivalences or some type of equivalences of some variation of GIT on the moduli space. So to kind of place me in the mirror symmetry point of view, what is happening on the A side here?
So we could go around this central point. And I think this corresponds to a symplectic Dane twist on the mirror.
That's interesting. Okay. And then usually when I'm thinking about these like variation of GIT, this is giving me, it's in the context of global mirror symmetry, where like if you look at, say, the quintic, the variation of GIT is telling you about symplectic deformations. And then the mirror has the hypergeometric, so that you have the mirror quintic, right? And the mirror quintic, has at the mum point has the large complex structure limit point is the it is associated to the quintic threefold, and then you have the LG model that's associated to the Gepner point, right?
Mm-hmm.
And here you have, I think I'm just very confused because you're doing the variation of GIT on the B model.
Yeah, so I think the confusion is that I'm assuming mirror symmetry for these examples. Yeah, but I mean,
it's curious because you have a whole C that's working on the Kähler moduli space rather than just like a one-dimensional ray and like toric GIT. Like the secondary fan here is just one-dimensional real.
mm-hmm.
So is this what happens when you say, okay, I'm just going to take a complexified Kähler form, and then on the real parts of the real line, I have dx1 and dx2, but I can go around this in the complexified Kähler moduli space to get between the two.
Yes, absolutely. So, I mean, you could also take this as a cylinder, right? So your real line times S1. So that S1 being an imaginary direction, but with an identification. So that's also a good way to look at this, yes.
Oh, okay, thank you. I know, like, okay, I'm with you now. Thanks.
Okay. Yeah, so I mean, maybe to say it another way for anyone else. So the left and right ends of these can be seen as large radius limits. Okay. So let me just remark another thing. So these monodromy matrices, if you look them up in the book, are written in terms of the parameters alpha I. They're rational functions of those. And you can get that in this picture by passing to so T equivariant. That's the significance of those parameters. So now let me sketch out the next case. So for d equals 4, the domain for a hypergeometric system turns out to be P2 minus the coordinate hyperplanes. So that's a 2 simplex in the sense that I have P2, these coordinate hyperplanes removed, and further I remove a quadric which touches like that. So not the best picture, but the important thing to note is we've gone up the dimension. This Kähler moduli space. And now S is now a late 19th century thing, Appel F4 hypergeometric. And it has 4 independent solutions. So now what I have is 4x4 monogamy matrices. And they're corresponding to the fact that the K-theory is now rank 4. So we have generators with certain phi degrees on each of my x's. And you can check that, well, let me not draw it in detail. But if you put x's here, you can start to relate paths in this space with these monodromy matrices. So let me say, in this case, star, this action of the fundamental group is a theorem of height, a student of Ed Siegel. But in general, of d greater than 4, then my m is going up in dimension each time, so it's d minus 2, in fact. You remove the simplex, and you remove some other stuff. This claim star is strictly open. we can start filling in this picture. We exhibited equivalences between these D's, but there's something more to do to prove the prediction of mirror symmetry. So,
Before you do this, I just want I'm not sure I understood everything. So one way I might think about these is that they give some sort of mirror maps, whatever. We have these like whatever, and they have some like monotonous behavior as you go around these special points or whatever, right? So what you're saying is that monotonous behavior, you can lifting it at a categorical level.
yeah,
Is that
exactly.
correct?
Exactly. So you can use these known monotony matrices. So these were written down in the ACEs. You can use them as a guide for how to write down this predicted function.
Yes. And so if I just think of mirror map, that how does the mirror map fit into it? Oh, that's a kind of that's a different story in some sense. I really like to do this kind of verification because it's like it's kind of like we understanding what's going on, but maybe mirror map is kind of irrelevant to this. It's just the monotony of those. Because is there also, I guess my question is there categorified mirror map? But maybe not. It's just some sort of silly coordinates. I don't know. Sorry.
Okay, so yeah, I'm also confused.
Yeah.
But yeah, we can.
But maybe
we can talk.
Yeah. But I think I
In a
understand
moment.
the kind of categorical lift.
Okay. Yeah.
Thank you. Sorry.
No, that's great. So yeah, so let me work out what to say. Two things. So no, PIT is not quasi-symmetric. And I say this because if it was, this lane star would be a theorem by Alpenleitner Sam, Stenko Vandenberg. So they have a condition called quasi-symmetry, which allows them to prove this sort of pi1 action. But it fails in this example. So retrospectively, that's explaining why we're talking on that. So I'd like to quickly state a result I just proved, which is some progress in this direction. So let me do that and then wrap up. So theorem take place of this d-2 simplex, which we've constructed, and write down the derived categories dxi, dxj, dx. So we have pointers fij, fjk, and f ik. And the result, and have some reason to believe that this is most of the way to star in this case, but it's a pretty thing on its own, is that the long root, f from I to j, and f from j to k, like this, is isomorphic to the short root up to Sj, an endo function of xk. So let me write that down, well, at least for d plus 4, because I think that will be enough to suggest to experts what the generalization is. So Sj is a spherical twist by the exceptional locus. So the bit in xk which gets contracted to the singularity with the twist. So if you remember, this exceptional locus in this case is the vi.
I'm confused. The object, the spherical object is defined. What does it depend?
So the spherical object is depends on the index.
Which is sphere. So it's an object in dxk.
It's an object in dxk, and xk contains an exceptional locus pbi times bbj. And this minus one, this non-trivial twist, corresponds to bbj. So let me put it in here, if it helps. So this is where Sj lives. So Sj lives on Sk, but it is dependent on the choice of another vertex in the face. It depends only on J. So
you're saying that for any I not reflective space,
let me say it like this. And it is quite difficult to get the conventions straight. Let me say it like this. So Si in this case.
So if I is J in this cat.
I is not allowed to equal J. So this is a choice of IJK distinct let's get this right. So if G equals 4, I have a 3 simplex. That's 1. And so I'll say Si, if I continue to describe the exceptional locus in xk by this, Si would equal the same thing, except now the non-triviality would correspond to the I factor here. Okay, so that's where I wanted to get to. Thank you very much.
Questions? Maybe.
Is Pi1M known, like, does it have a presentation as like a breakthrough or something?
Yeah. So no, but it does have a presentation by projecting in one direction. So in this case, we can project to a P1, look at what the fibers are. So the fibers are P1s with holes. You have a description coming from loops around those holes. As you move the fiber, how the holes move. So yes, one approach is to to work that out. There's also a goal to find approaches that are independent of that. Go more general. Test it with that sort of thing.
And you said on the mirror side, that should be the interest, that should be mirror to.
Yeah, so let me say a bit more there. That here we have a twist around a Lagrangian sphere. So an S3, I think so. The mirror is well known, and I believe you can match these functors with things in the mirror. So there's a paper by Polignano and others, which will give a good start from that. This, I think it's understood in principle, but not in detail, because I believe what you want is a family twist associated to some isotropic, co-isotropic. And so I don't know if details have been worked out. But those things are well understood on the B side. So we have a lot of candidates that we action.
So we have this Tyler, mute yourself.
Yeah, can you say a little bit about the proof of the theorem? Like, how does it go?
Yeah. So it goes by techniques of toric BGIT. So when I move between phases of the BGIT, I can construct an equivalence by choosing a window subcategory in the derived category of the stack associated to the GIT problem. So it uses a bit of new technology called partial windows. And those correspond to these paths. So if I start in a large radius limit here, and I go like this, that corresponds to a partial window. I mean, more obvious paths correspond to better known windows, but these sorts of things that are half in and half out of the quadric correspond to these partial windows. And so understanding those is the key to the proof.
Great, thank you so much.
Okay. Any other questions?
No, let's try the speaker again.